Welcome to episode 10 of our series Photoelectric Effect. Now we are ready to discuss the central research for which this whole story is being constructed, this whole session are being given, and that is Einstein's work on photoelectric effect 1905 paper, for which he was awarded this Nobel Prize in Physics just 100 years ago. Now, it's a common notion, and I also had that from my textbooks and from my schooling and then college teaching, that the experimentalists, stalwart experimentalists, they had done experiments on photoelectric effect, data were available, data were collected, and the existing theory was wave theory of light, and it was very difficult to understand those experimental results based on very successful wave theory of light. And among that was like the stopping potential or the kinetic energy of the photoelectrons being independent of intensity, and the linear relationship between this kinetic energy and the frequency of the light used, and all those things. And Einstein came with a theory which was very, very different from the existing well-established wave theory of light, and that was in terms of photons, and that could explain the photoelectric effect. So essentially Einstein did this research to understand, to explain, to provide a theoretical basis to photoelectric effect. That was the main reason of that particular piece of research. That is what generally believed. Now what we will see is that the fact is somewhat different. Alright, so we will take the original paper of Einstein, the English translation, of course, the original was in German. So we will take that original paper translation, and we'll see some parts of it and get a feel that what research was there and how it was related to photoelectric effect. Okay, so here is the English translation of Einstein's original paper, and this translation is published in American Journal of Physics, May 1965 issue. And here starts that Einstein's paper translated. Now the title, first is title. Title is concerning an heuristic point of view towards the emission and transformation of light, right? Then in this opening paragraph is something very interesting, and that I would like to point out here. Let me increase the size of the letters, and then you can see it here. Yeah, according to Maxwellian theory, let me tell what it is. In the Maxwell's electrodynamics, this light or electromagnetic radiation is a continuous function, okay, continuous spatial function in case of all purely electromagnetic phenomena including light. So light is considered as a wave, and that is spread over continuously in the space. So there is no discreteness. So while the energy of a ponderable object, this is some kind of a solid material object. If you think of the energy of a material object, since you have atoms and molecules, according to the present conceptions of physics, this energy is discrete. It is confined into those molecules, separate molecules. So there are a finite number of units of energy, and that make up the total energy. So Einstein is always looking for symmetry in nature. These are two different kind of things. If you are talking of material particles, energy is to be considered discretely located at certain locations where the molecules are there. Finite number of those energy elements. But if you are talking of radiation, then you say that no, the energy is continuously divided in the whole of the space. So that kind of asymmetry he always dislikes. Okay, so in that paper on special theory of relativity, Also, this kind of thing is there. This is the paper in which he has established that special theory of relativity. The title is On the Electrodynamics of Moving Bodies. And here also, in the opening paragraph itself, here, take for example the reciprocal electrodynamic action of a magnet and a conductor. So this experiment most of you must have seen or must have done as demonstration. Faraday's experiment, you have a coil, you have a magnet, the coil is connected to a galvanometer. So magnet moves through the coil, and then the galvanometer shows deflection, some current is there. And if magnet is kept fixed and the coil is moved, then also you have a similar deflection. Now the interpretation of the two are very different. And that is what is written here. Okay, for if the magnet is in motion and the conductor at rest, then the interpretation is that moving magnet creates an electric field and so on and so forth, and that electric field creates current. Whereas in the other case, if magnet is stationary and the conductor is moving, then there's no electric field, there's no electric field, but then this moving coil in the magnetic field of magnet creates some kind of an EMF, and that EMF, that electromagnetic force, electromotive force, that drives the current. So the interpretations are so different. So Einstein based this entire special theory of relativity on this asymmetry. The asymmetry should not be there, and therefore one single rule should govern this case as well as that case. Okay, so he has this liking all the time for symmetry. All right. So most of the things which are there in this paper, I do not understand, and therefore I do not expect you to understand. All right. But look at the structure. Look at the structure of the paper. Supposedly a paper to explain this photoelectric effect, but the title, then the first section. The first section is here. There are 9 sections in this paper. The first section is here, concerning a difficulty with regard to the theory of blackbody radiation. So here he says that with the existing theory, the total energy diverges, so there are problems in that and so on. Second section is here, concerning Planck's determination of fundamental constant. So uses this Planck's radiation formula, and then shows that okay, it matches well with the experiments, but in certain regions it may not, so etc. etc. So talks of that radiation formula. Then he says that concerning the entropy of radiation. So now that he's talking of entropy, thermodynamics of radiation, and for that he is deriving some expression. All right, so he is deriving some kind of expression here, developing that entropy. Then fourth section, out of 9, 3 have gone. Fourth, asymptotic form for the entropy of monochromatic radiation at low radiation density, so that entropy is continuing for radiation. And then he derives some equation. Here is that equation. We will be actually using this equation, but it is just reproduced later. So then he talks of molecular theoretic investigation of time of the dependence of entropy of gases on volume. So here it was entropy of monochromatic radiation, and here it is gas, real material particles, molecules. And for that he does some calculations, and then he comes out with the expression for entropy, and that expression is here. So I'll be needing this. I will need this. So I will write this on the board and discuss. But what it is entropy if you have a gas. Capital R is your gas constant. Capital N is that Avogadro number. So capital R divided by capital N is the Boltzmann constant K. V is the volume of that chamber in which this gas can spread out, and V naught, this is a small volume taken in this chamber. in this entire volume V, a small part V naught is just thought, and I'll explain what it is on the board, okay? But I'll write this expression for the gas. This is the entropy which he has calculated for the gas molecules, and number of molecules is n. And then sixth section, interpretation of the expression for the volume dependence of the entropy of monochromatic radiation. He has already derived that expression, and that expression is here. S minus S naught is this, which can be written in this particular form, So I'll write these two forms on the board and explain little bit more on that. So I have reproduced those two equations from that paper. This is the entropic change for a gas confined in volume V, normal gas, which has molecules. And I'll just tell the symbols. And this is the expression for entropic change when a monochromatic radiation of frequency nu is confined in this volume V. Okay. Now here this capital R is a gas constant. Capital N is Avogadro constant. So R by N is that Boltzmann constant, small k, that we write. And V is the volume of the chamber. Suppose this is the volume in which this gas is confined, or in the second case this radiation is confined, equilibrium with the walls. So that is this V. This V naught is an arbitrarily chosen small volume. The whole volume is V and this volume is V naught. So you choose a small volume V. And what are these S naught and S? They are entropies. If you assume that somehow these all molecules in this gas, somehow at some instant they are confined into this. There is no boundary here, remember, there is no boundary here. This whole chamber is, it has a volume, and in that volume we have chosen a volume here only. There are no boundaries. But suppose all the molecules are confined here at certain instant. What will be the entropy? So that entropy will be S naught. And in general, when it is all equilibrium and stable and all the molecules are spread over according to their choice, then the entropy is this S. So this is the meaning of this equation. And this equation, same thing. Again, you have a chamber of volume V, and this monochromatic radiation of frequency nu is spread over this. And the same meanings, this V naught is this small V naught, and suppose all the radiation somehow gets confined into this small V naught, then what will be the entropy? That is this capital S naught. And when the radiation is taken its own course of action, it is spread in its own way, then the entropy is this S. Now compare this and compare this, these two. S minus S naught, R by N, log V by V naught, V by V naught, to the power small n here, and to the power this big factor here. Okay, same structure. Now this E by beta nu R by N, this is taking the place of this small n. So if you have energy distributed at these small n centers, these are molecules, remember there are small n molecules in this gas, and energy is located at those molecules. So energy, total energy, capital E of the system is distributed at these n discrete centers, and in between there is no energy. Alright, and this is taking the place of small n if it is radiation. So that means this monochromatic radiation can be thought of, compare these two, can be thought of that the whole energy of this monochromatic radiation, electromagnetic radiation, is confined at these many centers in this whole volume, not in the entire volume continuously. But in this volume, there are these many locations. Location here, location here, location here, location here, location here, location here, location here at one instant, at one given instant. So the total number is small n, that is this. And whole energy of the radiation is either here or here or here or here or here or here. Okay, and the total is E. Capital total is E. So this whole energy of this electromagnetic wave is not continuously distributed over the volume, but it is confined at certain definite locations, finite number. How much is the number? Is this? These are your energy quanta. The next question we can consider is, if this total energy capital E is distributed in these many locations, which we call quanta, at a certain instant, remember, these are all moving with that speed c. So if the total energy is distributed in these many centers, how much is the energy at each center individually? So if I assume that this is same for all quanta, if this energy is same, then the energy per quantum, how much it is. So if I do that, and if I call it, say, since we have already used this E here, let me call it some E0. What is this? This is energy per quantum. We have these many quantums, energies are located at these many centers. So at each center, how much is the energy here? How much is the energy here? How much is the energy here? And assuming that all these are having the same energy, this energy will be equal to E divided by this total energy, and that divided by this whole thing, E, and then by beta nu capital R n, and that is just this, beta R by n. It is just this, beta capital R by n, and then mu. Alright, what is beta? Beta appears in that Planck radiation law. If you have noticed in this Einstein paper also, that expression is given, Planck's radiation law expression is given, and there you have two constants, one is alpha, one is beta, and that alpha and beta, they are fixed. Planck has obtained the value of beta and alpha. Actually beta, alpha and beta are related, so that the value of beta is taken which matches with the experimental curve of intensity and this side wavelength. So how that that energy of this radiation is distributed in different wavelengths, that is spectral distribution, which goes through a maximum, to match that what beta is needed. Alright, so the beta is fixed quantity, once again fixed quantity, and in fact universal constant. Okay, then R is the gas constant, normal gas constant. N is Avogadro number, so R by N is Boltzmann constant. Everything known. So this is known, and this is universal. It does not depend on anything else, and therefore, if you call this H, this is equal to H times mu. So what is the picture? What is the big picture? The big picture is, though it is electromagnetic radiation, though it follows that all diffraction, interference, all those things can be very well explained by telling that it is a wave, classical wave, no quantum character. And still it can be regarded as, you can also take this view that this energy of this radiation is not continuously distributed as demanded by the pure wave picture. But in certain cases, it can also be treated as a separate energy quantum here and there. Alright, and there is no conflict as such. Both coexist, because ultimately, what is this new? Ultimately, what is this new? This new is the frequency. Frequency of what? Frequency of what? This frequency or this wavelength frequency are related. This wavelength, this frequency, they are all coming from the wave picture. Alright, so that interference, diffraction, that tells me, okay, this is the wavelength, this is the frequency. Bring that frequency from there and then construct these quanta with these energy, h nu, h nu, h nu, h nu, h nu. If your radiation is monochromatic with certain frequency, certain wavelength, then okay, this. If it is a mixture, then fine, we have varieties of photons of different h nus, So that's the kind of picture it emerges. Okay, so we'll continue with this. We will explain in little more what does it mean and how it finally explains photoelectric effect and all those things in the next episode.